So maybe we should proceed to our next speaker, Dr. Nabilah Abughazalah. So she's an assistant professor at Prince Noura University in Riyadh, Saudi Arabia. She's done work in her master's on Lie algebra, and for her PhD at St. Andrews, worked on semigroup theory. And she will be speaking today about central series of associative algebra. And these are some other mathematical conditions for semigroups.
Thank you.
Thank you. Yeah.
Hello, I am Nabilah Abughazalah. I am an assistant professor at Princess Noura University. And here in MIT, I am working with Professor Abughazalah. Since I came to MIT, we have been working in two directions. A lower central series of associative algebras, the first direction, and after that, the finitest conditions for semigroups. And the idea behind these two different things that I am originally working on finitely presented semigroup, which means a semigroup has finite generating set and finite relations. So we take these relations and we study the lower central series of semigroup algebra modeled by these relations. I'm going to start by some definitions. An associative algebra over R is an R module A with an R bilinear associative multiplications. Take the pair A and B to the product of A and B. We say that A is a free algebra over R. It's a free algebra over R is an associative algebra that is generated over R by a set of generators with no relations. That's why we call it free. And we denote it by AN. If AN is a free algebra on generators from x1 to xn, AN spanned by all words a letter from x1 to xn. For example, if we have A2, which is a free algebra on two generators x and y, then it will be spanned all words a letters x and y. From the 0 degree is 1, and the first degree is x and y, and the second degree is x squared, xy, yx, y squared, and so on. We can take the coefficients in the rational numbers q, integer z, or finite field. The commutator C and D is the product of CD minus DC. And if we have a commutator of BCD, so first we do the inside CD and then we do all together. The commutator of AA equal to Z because AA minus AA is 0. The Jacobi identity is given by this equality. We say that A is Lie algebra if it's A are R module with a bilinear bracket operation A and B such that this conditions and this satisfies. Lower central series, if A is a Lie algebra, we define a series of Lie ideals. LA is A, L2 of A is the commutator of A and L3 is the commutator of A, and so on. From here, it's clear that L3 is a subset of L2 is a subset of L1. For example, I hear a very simple example of a free associative algebra over x and y over the field Z. Now in L1, that's mean from the definition that we just have A. So in the degree 1 we have x and y, and degree 2 is x squared, xy, yxy squared, and degree as is shown here. In L2, that's mean we don't have something of degree 1, and we will start from degree 2. And we will have the commutator x or y because xy minus yx is something of degree 2. L3 is will be 0 of degree 1, will be 0 on degree 2, and we will start from degree 3, and so on. Now, after giving the definitions of lower central series, we have some other series we denoted by BI, which is the quotient of Li by Li plus 1. And Mi is the two-sided ideals generated by Li, and Ni is the quotient of Mi by Mi plus 1. Now, why are we studying the lower central series? Now, the non-commutative algebra are much larger and more complicated than commutative ones. So, to understand their structures, we may study their lower central series. So, how we study it? Now, we have conjectures and theorems. This comes from data we obtained by a magma program designed to solve problems in algebra and number theory. First, we wrote a specific program, magma, which gives us the rank of BI and NI. And then, so we have the input, we have the relation that we multiply and their degrees. The output we have consists of several lines, each present the rank of NI or BI for some I's and D's. And then the information, we put it in a tables. For example, it's a very simple example. It's a free algebra over in two generated xy over z, mod by the relation x squared equal to 0. So here, by using the program and running the code, we get something like this. And here it's clear that there is a patterns from 3 and so on, and from 3 here, 3, 3, 3, and from 4, all 3s. So from these informations, we can, this yields the conjectures about stabilizations of rank NI, which is something like that, and they try to prove something like that. So from the data we have, we give a conjectures and trying to prove it. In our example that I have been working on is a free algebra in two generated xy mod by polynomial of degree 3. So here, things getting harder and more complicated than the previous one. Here the patterns is not as clear as before. And this is for BI, and this is for NI. And the other example we worked also here, but it takes a lot of information here. It's a polynomial of degree 4. Also still, we don't have the patterns that we want. We trying to improve the program. This program runs until 11 and 12. And sometimes it takes 2 days and stops. So we're trying to improve this program until 16 or 17 and get the conjectures that we want. And still we trying to improve these programs. This part is related to the computer and magma and codes part. Now, in the other parts here, we are working on finite conditions of semigroups, which is related to pure algebra. And finite conditions mean that we say this property is finite condition for semigroups if it's all finite semigroups satisfy this property. So, and in semigroup algebra now, it's easier to study the finite semigroup than the infinite semigroup. And we know many properties for finite semigroups, like finitely presented, finitely generated, reasonably finite, but we don't know that on some other big or infinite semigroups. So in our semigroup here, we have S, which is a disjoint union of the free monogenic semigroup. The free monogenic semigroups means the semigroup was generated by one element. And then we get this semigroup, which is basically a power of a generator. It's very big, it's infinite, it doesn't have idempotent, it's not constellative, so there is no big things that helps you to prove some theorems. But it still has some good properties. If we have two relations like these twos, here a to the power I, b equal to c to the power j, and a to the power k, b equal to c to the power l, then these two relations produce another relation, which is this relation for every n in n. That means this relation gives us an infinite number of relations. That means that these relations cover infinite number of relations. The other property that we have is if we have these relations, and here is A and here is A, then we prove that R is less than or equal to T. So by these two relations, or these two lemma, we say that we prove that if we have a relation that like this appears just once or infinite number of them. So that means that arithmetic progressions start to appear here. Past work on this semigroups, we proved that this semigroup is finitely presented by this presentation, and it's finite generating set and finite number of relations. Don't worry about all these symbols. It just it's a power of a generator. And we proved that, but it's a big presentation. It's proved the theorems, but the problem is this presentation doesn't give me the classification of all these semigroups. We proved that this semigroup is reasonably finite, which means that there is a homomorphism from the semigroup we have to a finite semigroup, such that any two elements in the semigroup, their images are not equal. In the other direction, we proved that this semigroup, if it's disjoint unions of two copies or three copies, we classify all these semigroups. I just mentioned here the three copies. So up to isomorphism and anti-isomorphism, every semigroup S is a disjoint union of three copies of the free monogenic semigroup DGH, if and only if it's isomorphic to the semigroup which is defined by one of the following presentation, and we have here 9 presentations. Now, when I mentioned that it's 9 presentation, it doesn't mean it's 9 semigroups. So here in the first one, you can see the IKP is n, so they are infinite number of them, but they take these types. And in the disjoint union of two copies, we proved that it has 2 presentations. Now we are trying to prove that classify more than 3, 4 or 5, but still it's need more work. Current work, decidability and linear growth don't work with Pavel. Now decidability is something related to algorithms and to find a solution for a problem in finite number of steps. So the first problem that we proved, the word problem, we say that S, which is finitely generated, has soluble word problem if there exists algorithm, which for any two words, U and V and S, we can say U is equal to V and S or not. That means we have algorithms and we have finite number of steps. With these steps, I can decide if U and V equal to V and S or not. And this is the theorem. Every semigroup, which is our semigroup we work in, has soluble word problem. The sketch of the proof, the algorithm, we have the input is 2 words, U and V, and because it's in S, that means that it's a product of a power of a generator, something like this. So U is a product of a power of generators, and V the same. The output I want to know is U equal to V or not in S. So the first step, specify the big presentation that we talk about. So to specify this presentation, I need to know the fixed point that we start with in the arithmetic progressions. And we will take D, the least common multiple of all these Ds. And then we prove that if we have a relation like that, then we can determine C to the power J in infinite number of steps. And this is the key of this proof. Then we transfer U to its normal form by taking the first x1 to the power I, which is one here, with the second element, and then do this I2 steps until we get rid of all these x's, and we end up with xl to the power lm. Transfer V to its normal form similarly to step 3. So we get that V is also x index g to the power jn. If I equal to j and lm equal to jn, then u equal to v. Otherwise, u is not equal to v in S. So we prove that this semigroup has a soluble word problem. The other property related to decidability is the sub-semigroup membership problem. We say if we have a finitely generated semigroup and we have a sub-semigroup of S, which is T, and I was given an element X, and you told me, is X in T or not in a finite step? Can you answer this? So we say yes, we have an algorithm, this is the theorem. We have which says that this semigroup has soluble sub-semigroup membership problem. But to understand this theorem, first we have to know that to understand very well the behavior of sub-semigroups of N. Now any sub-semigroups of N has the form F union D, which basically it's finite set and infinite set, and this set has a rule which controls this infinite set. So for example, if we have this sub-semigroup from N and it's generated by 4 and 7, then when you evaluate that, we have this set which is finite, and then we have this set which is infinite. But here's a rule, here's a difference, which is 1, and here it's just finite set, and there is finite numbers of gaps. Just to, I will mention that after. So the algorithm is, now the input we have T, and we have the element that you asked me about it, if it's in T or not. And the output is X is in T or not. So the first step, we will take a very small sub-semigroups from each free monogenic semigroup. And then we will see if the disjoint union of these U's give me T or not. If yes, we stop. We've done. If not, we are going to the next step. So that means there's element is not in our semigroup. I will add this element. And when you add this element, that means you will add it to the finite set or to the infinite set. If you add it to finite set, that means you can do this just finitely many times because the gaps are finite. Or you will add it to the infinite set, which has a rule and a difference. And the difference, you can listen the difference just finitely many times. Then we do this again. I will examine my semigroup. Is the disjoint union give me T or not? If not, if yes, we stop. If not, I will keep adding these elements until I reach to the final description, which give me all these U's equal to T. And as I said, this will stop because the finite numbers, it's finite, so you keep adding and you will stop, or you will listen the difference and you can't do this forever. The last property that you prove, the linear growth. We say that the semigroup S has linear growth if this set, rank of this set is less than or equal to a fixed point n for some C, where this set is all the words which is of length less than or equal to n. The techniques of this theorem, we define a function from this set to A, and we define a function from this set to Z by the formula this. Okay? So also here, don't worry about all these symbols, it's just the power of a generator. Then we take all I, which give me Z. I mean, when we start arithmetic progressions, and we put it in a set which is E, X, Y, Z. We say that Z is XY persistent if this set is infinite, which means that an arithmetic progression starts here. The lemma 1, if Z is XY persistent and this set take this formula, then there exists a rational number mxyz such that this satisfies. Now we prove that if mxyz, we prove that this rational number is independent on x. The function fxyz is periodic starting from some place. Lemma 2, if xyz in A, if z is y persistent and y is X persistent, then Z is X persistent. Here, it's give you the feeling that we are going to define a relation which is a transitive relation. And this is the relation that I'm talking about. Now we define relations, be reflexive and transitive, such that these two conditions satisfies. Then there exists a positive integer function, dy, bigger than or equal to the product of the rational number by dz. And this is the key in this proof. Every semigroup, which is a disjoint union finitely many copies of the free monogenic semigroup, has linear growth. And the sketchy proof is we have the set of all words can represent by word of length less than or equal to m. We prove that the rank of this set is less than LKM, where LK is the C that we talked about before, and LKM taking these values. Now, K here, because the arithmetic progression is finite, the finite number of them, we have many Ks, and then we will take the maximum K, which is this K. All these results and theorems appears in these publications and already submitted to journals. And based on this, we are trying now to understand more the relation that appears before the arithmetic progressions. And we are trying also to classify this presentation, not just for 2 copies or 3 copies. And also, as there is a connection between linear, the semigroups have linear growth, and our semigroup. This is our work, and finally, I want to thank the many people who've been involved in this project. First, thanks go to my wonderful supervisor, Professor Pavel, who was with me, not just in mathematics, but also in facing the toughest winter I've been through. Also, I want to thank MIT and Aramco for giving me this opportunity to be here, and Princess Noor University for supporting the fellowship, and of course Kate and Teresa for their help and kindness. Thank you very much. Thank you for coming.
Thank you, Dr. Nabilah, for the presentation. I was going to say, we use Lie algebra in controls. We're looking at how to formulate the input-output relationships. But in that case, we do use not polynomials, but from differential equations, right? And then functions, and usually that are nonlinear.
Yeah.
We try to use the algebra to, as I said, finding the input-output relationships, and then you get some control systems. But anyway, that is, I think, the connection that I can see. The rest of it was a little bit blurry to me. So. Any questions or comments? Yeah. Yeah. So.
So I have a comment. I'm actually part
Please.
of that group. It was very great to have her, and there was one small correction I want to make. So she said about the semi-group, started talking about semi-groups and said it was joint work with me, but actually only the second paper is joint with me. And the first paper, number 1, is just by herself.
Yeah, but you editing the paper, so thank you very much.
Yeah. So one of the things that was interesting to me, that I'm comparing this with some of the things I know into controls. You did mention then starting with, let's say, some relation,
Yeah.
right? And then you have an algorithm or some proof to say whether a result can be obtained
From the data.
from the data,
Yeah.
and that there would exist an algorithm. So this is interesting that you have a relationship in data, and then to say whether one can get to a certain result, that there is an algorithm in between that will allow you to get there,
Yes.
but does not necessarily say what the algorithm is. Is that correct?
Yeah, that's right. Yeah.
Yeah. In
First,
control-
we just give the data
yeah.
and
It's very interesting because in control you have something very similar in how to take the system from one state to another. We call it controllability. And then the approach is just to say whether it is feasible. but without stating, what the method actually that we take.
Yeah, exactly.
So, so here, if you can maybe just, I was curious on the steps, or maybe just very briefly on how one gets to that result, in a sense to say that there is a way, but not necessarily stating that way.
For example, here, you can see the, yes, for example, here we have the patterns.
Yeah.
Start from 3, for example, in the first line. And from the second line, start from 3, from 4. And so on. Here, from this, they get yields these that we have this conjecture obtained from, do you understand me? So this is the conjecture, we get it from the data. That Nij equivalent to Nij plus 1 for j, and this we get it from the data here. And then we try to prove it.
So just to clarify, so this particular one can be proved, is known how to prove, but something slightly more complicated, like for the next picture, we already don't know, and it's a question of
Failure is still
matching theoretical tools with computation. Sometimes we can do something for high degrees by theoretical tools, and then in low degrees we have to compute by computer. So it's a computer assisted.
I see, yeah. Any other, yes.
I want to ask a question. I'm in engineering, so I think if you spend more time about how we can apply this theory in engineering, I think this is a task that getting really abstract mathematics. I'm sorry for pushing on these abstract things to something applicable. I think this is becoming really a good thing, especially that this is innovative.
I hope so.
I hope
Always
so
in mathematics, it's pure. I hope to do something applicable, as you say, because mathematics is just theorems and something very abstract.
So this is a kind of pure algebra, so for every particular problem it is hard to say what its applications are. But in principle, for example, this decidability and work problem things, this is, belongs to the field of theoretical computer science. And this in principle has very important applications for computers.
It's connected to meta theory and languages.
I just want to take it easy on this kind of thing, because I understand that all the people in algebra, we have something that FUBM or study, they are working the same way. But as I found it, even in the undergraduate or the graduate, our students, they are not taking mathematics as something acceptable. If we can get the linear program or something that make it easier, and if we start on this college level, I think it should be really good. I think FUBM, we spend 1 more credit hours on some of the applied mathematics to see the application that it is suitable in the engineering. So
it's easier in applied mathematics. Yeah, but in pure mathematics, I think it's still. In applied mathematics, it's easier to,
And I hope that this is also, if you think about it, how we can just apply another way. I don't want to be confronted with the mathematics.
Thank you. Yeah. Dr. Zubair, did you have a comment?
Yeah, I was also going to ask a question in similar lines. I do know that algebra has a lot of applications in partial differential equations. Developing similarity variables, so you can reduce partial differential equations to ordinary differential equations. So this what type of thing engineers we are looking for. And can we apply such techniques to some of our problems which can help to solve?
I think it's not easy to say yes or not, because in pure algebra, it's still far from engineering and these things.
Well,
maybe lower.
the semi-group business does not have applications to partial differential equations, but the one about lower central series, in general, the algebra theory, as was pointed out, does have applications to differential equations. In fact, the algebras appeared essentially from trying to find symbols of differential equations. So this is how Sophie found the algebras. Yeah, in that particular work, actually, the interesting thing is it's an algebraic problem, but the insights to solve these problems come from differential geometry and differential equations. So somehow it's the other way.
I have one, maybe just a brief comment about this. In the part when you were talking about you had a group and then you picked
the small
the
subsets.
small subsets, yeah. Is it possible that a person can pick the semi-subsets in a way that in the end it doesn't lead to an answer, although there is a solution?
No, because each subsemi group, which is
Yeah.
small,
Yeah.
we take it,
Right.
and then you will test it. Is it the disjoint tuning give me T, and if
Yeah.
not, you will add the element that's missing, and you will add it to
I see.
the gaps. And this
Okay.
gap's finite, and the D is the difference. You can listen the difference finitely many times, so you will stop at the end.
I see. Okay.
So these semigroups, which consist of several copies of the free homogenic semigroup,
Yeah.
they're in fact very rigid. They're very constrained, and there are not that much freedom there. And eventually, maybe thanks to further work by Nabilah,
Yeah.
we will understand them more or less completely, but not yet. And so at the moment, we're just trying to find their properties that would help us have a definitive classification and understanding of
Right,
them.
yeah.
But I expect that in a few years we will have a completely explicit picture of them.
The reason I ask is because I'm imagining a problem that is very, very large in terms of data, right? And then the process of selecting, these semigroups,
Small, yeah.
the small, right? Anyway, that's the reason why I asked it. But anyway, so let's thank Dr. Nabilah. This time I'm not going to forget. So again, on behalf of MIT and our sponsors, I'd like to present a small gift to you.
Thanks. Thank you.
Thank you so much.
Thank you.
Thank you. Yeah.